In this video, we will discuss an application of exponential growth, exponential decay. So something commonly encountered in application would be having some quantity, let's call it y of t, which is a quantity of y at a time t. So think it could be something like, say, the size of a population at a given time, or maybe the mass of an object at a given time. And what we might frequently encounter is the idea that the rate of change of y is proportional to the size of y. So the rate of change, that would be dy dt, is proportional to. And when you say that two quantities are proportional, what that means is that they are equal up to a constant, where that constant k would oftentimes be referred to as the constant of proportionality. Now it turns out that this dy dt equals ky is something that we call a differential equation because it's an equation involving derivatives, but really it's the topic of an entire semester course that one would take after Calculus 3. And for this case, the only solution is going to be an exponential function of the given form here, where we think of y of 0 as being the initial amount. That could be population or size of a sample. Now, something that's definitely worth observing is when k is a positive quantity, this would be exponential growth. You'll be getting bigger. And when k is a negative quantity, the situation being described would be exponential decay. And let me just give you a little idea of where the solution of this differential equation comes from, because it really only involves ideas that we've previously encountered. So let's solve this differential equation where we're thinking, the initial size is something like y of 0 equals, and we'll just call it y naught for convenience. So we're starting off with dy dt equals ky. And up to this point, we oftentimes encounter something like dy over dt and think of it as being a single quantity. But it turns out you can think of these as being separate entities. You have the differential dy, differential dt. So what I could do is maybe put all of the y's on the left, all things involving t's on the right. So divide both sides by y, multiply both sides by dt. And when you see it in this form, it looks as though something is missing. To me, it really looks as though we should throw in some integration symbols. And when you integrate, you have the natural log of y equals kt plus c. So remember, k is a constant. And at this point, you might object and say, you need your absolute values. And technically we do, but we're thinking of y as representing the size of some quantity, so it's going to be positive, and we can maybe lose those absolute values. And if two quantities are equal, e raised to those powers would be equal. So e to the natural log leaves us a y on the left, and using properties of exponentials, on the right we could think of this as being a to the kt times e to the c. And here, e to the c is a constant. Let's go ahead and just call it c1 times e to the kt. And the last remaining thing to do here is to just maybe decide exactly what this constant c1 is going to be. So we know that y naught is equal to y of 0. So if I look over at my solution here and I plug in 0 for t, you have c1 e to the 0. E to the 0 is 1. So that constant c1 that we have is really just equal to y naught. So y of t, the size of our population, is equal to y naught, which is the initial size or population, times e to the kt. So just giving you a small bit of intuition of where this formula comes from. And note, from a differential equations perspective, something you all might encounter in the future, what we've done is we've solved something which is known as a separable differential equation. So let's go ahead and look at maybe a few typical examples involving exponential growth and decay. So the first typical type of example involves finding things like half-lives. So the half-life of radium-226 is 1,590 years. A sample starts off with an initial mass of 100 milligrams. What we would like to do is find a formula that represents the mass that remains after t years. So we are going to have m of t, I'll introduce as my notation, which will be the mass of our sample after t years. And when you're dealing with decay, as we have in this case, it's going to be something where you have exponential decay. So our mass, m of t, when we're dealing with half-life, is going to satisfy dm dt equals k times m. So it's decaying at a rate proportional to the amount present. And additionally, we know that we're starting off with 100 milligrams. So m of 0 equals 100. We also know that the half-life is 1,590 years. So we know that the mass after 1,590 years is going to be half of what you started with. So 50. So the first initial value combined with this differential equation tells us the solution is going to be m of 0 times e to the kt. And then the second initial value is going to allow us to solve for this unknown constant k. And hopefully what we see is that this constant k is in fact negative, so that we have the decay that we hope to see. So plugging in, we know that 50 is equal to m of 1,590 years, which is 100 e to the k times 1,590. So dividing both sides by 100, we have 1/2 is equal to e to the k times 1590. And what we would like to do is solve for k. But in order to get to k, we need this exponential to go away. So we take natural logs of both sides. So natural log of 1/2 is equal to k times 1590. And continuing on, if we isolate that k, it's going to be the natural log of 1/2 divided by 1,590. And just to observe that it's really negative, let us note that natural log of 1/2 is really the natural log of 1 minus the natural log of 2. Natural log of 1 is 0. So what we are left with is minus the natural log of 2, which is a negative quantity because natural log 2 is positive, the negative out front, divided by 1,590. And we're done. We can now combine things together. We have our formula for the mass in terms of the unknown constant k, and we've solved for k. So the mass of the sample after t years is 100 e raised to the minus ln of 2 over 1,590 times t. And just an observation to make, once we kind of apply this idea of exponential growth and we come up with our formula, the remainder of the problem, which is really the significant amount of work here, is an algebra problem. This is something that we encountered back in pre-calculus, except we are most likely given this formula to start. One more example, this time involving exponential growth instead of decay. A population of bacteria is growing at a rate proportional to its size. So immediately, before reading any further, I'm going to let P of t be the population, and looking further at it's in terms of hours. So after t hours, and the rate of change of the population is proportionate to its size. So it's exactly one of these equations that we were talking about. So what they tell us is at noon, there were 10,000 bacteria, and after 2 hours, there are 40,000. So that would tell me that we're sitting time 0 to be noon with 10,000 bacteria, and 2 hours later, is when we would have 40,000. And really in terms of the sit-up, what we see here is everything we need to solve the problem. And at this point, it's really no different than our previous example as well. So let's see here. dp dt equals kp with p of 0 equals 10,000. So immediately we know what the solution of that differential equation is going to be. P of t equals initial population, e to the kt. And then we need that second piece of data to solve for the k. So when we plug in 2, we get out 40,000. So 10,000 e to the k times 2. So if we go ahead and divide both sides by 10,000, 40,000 over 10,000 is 4, and that equals e to the k times 2. So the natural log of 4 is 2k, which tells us k is equal to the natural log of 4 over 2, which you can check is a positive quantity, so we really do have exponential growth. So in terms of our population, the population after t hours is going to be 10,000 e to the kt. So e to the natural log of 4 over 2t. What we would like to determine is not just that formula, but answer a question. How many bacteria will be present at 5 o'clock? So in order to see that, 5 o'clock would correspond to 5 hours after noon. So this would be 10,000 e to the ln of 4 over 2 times 5. And plugging this into our calculator, we get that the approximation here is about 320,000 bacteria.